What if I told you that our brightest minds have just learned how to listen to the echoes of the quantum world? What if by doing so, they unlocked a power so immense it makes today's fastest supercomputers look like ancient relics, and in the process, turned the key on a new era of human discovery? This isn't science fiction. This is the story of a breakthrough that just changed everything. This is the story of quantum echoes. Imagine the fastest, most powerful supercomputer on Earth. A machine the size of a tennis court, packed with processors, consuming enough electricity to power a small town. Let's call it Frontier. Now imagine giving it a problem so fiendishly complex it would take Frontier over 3 years of non-stop dedicated work to solve. That's the scale of computation we're talking about. Billions of calculations per second, for years on end. Just recently, Google unveiled a revolutionary discovery. A quantum achievement they call quantum echoes. Running on their new quantum processor, the Willow chip, this new method solved that very same problem. Not in 3 years, not in 3 months, or 3 days. It did it in just over 2 hours. Let that sink in. A task that would take our best classical supercomputer years was completed in the time it takes to watch a movie. That's a speed up of 13,000 times. But here's the part that truly changes the game. The detail that elevates this from a stunning feat of engineering to a turning point in scientific history. For the very first time, the results are verifiable and repeatable. This isn't just about being faster. This is about being right. It's about getting a trustworthy answer from a machine that operates on the very edge of reality, in a realm governed by the strange and beautiful laws of quantum mechanics. For decades, that was the missing piece of the puzzle. Now, with quantum echoes, that piece has clicked firmly into place, and the picture it reveals is breathtaking. To understand why this is such a monumental shift, we have to look back at the short, strange history of quantum computing. For years, quantum computers have been like brilliant, erratic magicians. They could perform incredible feats, dazzling party tricks that hinted at their immense potential. They could achieve something called quantum supremacy, a technical milestone where a quantum computer does something, anything, that a classical computer practically cannot. Google first claimed this milestone back in 2019 with their Sycamore processor. It was a landmark moment, a proof of concept. They performed a calculation so abstract and specific that it was essentially meaningless. A random circuit sampling problem that had no real-world application. More importantly, there was no practical way to check if the answer was correct. Imagine a mathematician shouting out the billionth digit of pi. It's an impressive claim, but without a way to verify it, it's just a number hanging in the air. It's a clever demonstration, a brilliant party trick, but you wouldn't build a bridge based on it. That's where the skepticism in the scientific community has been rooted. What good is an impossibly fast answer if you can never be sure it's the right answer? This new breakthrough with quantum echoes shatters that barrier. It's the moment the magician steps out of the stage lights, hands you their notebook, and shows you the elegant, repeatable mathematics behind the trick. The partikix, magic, is gone, replaced by something far more powerful. Verifiable, trustworthy science. Quantum computing has finally graduated from abstract experimentation to a true scientific utility. A tool capable of reliably studying nature itself. So, what makes this so incredibly difficult? Why has it taken decades of work by thousands of the world's smartest people to get to this point? The challenge lies at the very heart of the quantum world. Classical computers, like the one you're using now, work with bits. A bit is a simple switch, either on or off, a 1 or a 0. It's dependable, predictable, and robust. Quantum computers, on the other hand, use qubits. And a qubit is a whole different beast. Thanks to a principle called superposition, a qubit can be a 1, a 0, or both at the same time. Think of it like a spinning coin. While it's spinning, it's not heads and it's not tails. It's in a state of potential, a blend of both possibilities. This ability to exist in multiple states at once is what gives quantum computers their exponential power. With just a few hundred qubits, you can represent more states than there are atoms in the known universe. But this power comes at a tremendous cost. Fragility. The quantum state is unbelievably delicate. The slightest disturbance from the outside world, a stray magnetic field, a tiny vibration, even a particle of light, can cause the spinning coin to wobble and fall. This collapse of the quantum state is a phenomenon called decoherence. It's the arch nemesis of quantum computing, the constant, pervasive noise that corrupts calculations and turns beautiful quantum potential into useless static. For decades, the story of quantum computing has been a battle against decoherence. It's been about trying to build a perfectly silent, perfectly still, perfectly isolated chamber, where these quantum spinning coins can do their work undisturbed. Getting reliable, repeatable answers from such a fragile system seemed for a very long time to be an almost impossible dream. Let us revisit that 2019 quantum supremacy claim to truly appreciate the leap we've just made. While a monumental achievement in physics and engineering, the computation itself was, for lack of a better word, hollow. It was designed to be something a quantum computer could do that a classical one couldn't, but the task had no inherent meaning or utility. It was like building the world's most powerful rocket engine, strapping it to a test stand, and firing it up. The sheer force and fire it produces are incredible, a testament to your engineering prowess. But without a rocket body, a guidance system, or a destination, it's not actually going anywhere. It's a spectacular demonstration of power, but it's not a useful vehicle. The 2019 experiment proved that quantum power was real. But the new achievement with quantum echoes builds the guidance system. It gives the rocket a rudder and a map. By producing data that is not only calculated at incredible speed, but is also trustworthy and scientifically relevant, it transforms the quantum computer from a powerful test engine into a vehicle for discovery. This is the crucial difference between supremacy and advantage. Supremacy is a theoretical victory on an abstract battlefield. Quantum advantage is about solving a real-world problem better than any other tool we have. And that is precisely what has now been achieved. So, how did they finally tame the quantum beast? The answer lies in an incredibly clever and elegant algorithm Google's team developed, a method they named quantum echoes. The inspiration for it is something we experience all the time: echolocation. Imagine you're in a completely dark cave. To understand its shape, you shout. The sound travels forward, bounces off the walls, and returns to you as an echo. By listening to the timing, direction, and quality of that echo, your brain can build a detailed map of the unseen space around you. The quantum echoes algorithm does something remarkably similar, but on a quantum scale. Here's a simplified way to think about it. First, the quantum computer runs a complex operation forward in time. This is like shouting into the quantum system. Information spreads out through the qubits, interacting and entangling in incredibly complex ways, like sound waves spreading through a cave. Next, they apply a tiny precise kick or perturbation to a single qubit. This is like placing a small object somewhere in the cave after you've shouted. Then, they do something that sounds impossible. They precisely reverse the operation, effectively running the quantum evolution backward in time. In a perfect classical world, this reversal would simply undo everything, bringing the system back to its exact starting point, as if the shout had never happened. But in the quantum world, that tiny Ahuan kick they introduced creates a subtle interference pattern. The forward and backward waves don't perfectly cancel out anymore. What comes back is a faint but measurable echo, a signal that carries rich information about how that tiny kick spread and scrambled throughout the system. This echo is measured through a complex physical quantity called the out-of-time ordered correlator, OTOC. The OTOC is a way to measure the quantum butterfly effect, how a small localized disturbance grows and propagates through a complex quantum system. For years, calculating OTOCs for anything but the simplest systems was considered impossible for classical computers. But with quantum echoes, Google's team turned this impossibly complex calculation into a powerful new scientific instrument. An algorithm this sensitive needs hardware of almost unimaginable precision. At the heart of this entire feat lies Google's newest quantum processor, the Willow chip. To call Willow a chip feels like an understatement. It's more like a scientific masterpiece. Its 105 superconducting circuits, which act as the qubits, are engineered for extreme stability and incredibly low error rates. To function, the chip must be kept in a massive chandelier-like refrigerator that cools it to temperatures colder than deep space, just fractions of a degree above absolute zero. This extreme cold is necessary to minimize thermal vibrations and keep the demon of decoherence at bay. It is within this silent, frozen sanctuary that Willow performs its magic. The chip's design allows it to perform trillions of stable measurements, a feat of engineering that is essential for amplifying the faint quantum echoes that would normally be completely lost in the background noise of the universe. Think of it like this. The quantum echoes algorithm is the sheet music for a beautiful, intricate symphony. But the Willow chip is the Stradivarius violin required to play it. Without an instrument of this caliber, one built for precision, stability, and clarity, the music would just be noise. Together, the algorithm and the hardware create a harmony that allows us to finally listen to the subtle, hidden melodies of the quantum realm. An algorithm that can outperform a supercomputer is one thing, but can it do real, useful science? To answer this, Google collaborated with researchers at UC Berkeley to put quantum echoes to the test in the real world. They used it to tackle a fundamental challenge in chemistry, mapping the structure of molecules. Their partner in this experiment was a well-established scientific technique called nuclear magnetic resonance, NMR, spectroscopy. NMR is a workhorse of modern chemistry, used to determine the structure of molecules by probing the magnetic fields of their atomic nuclei. It's an incredibly powerful tool, but it has its limits. The Berkeley team provided NMR data for 2 complex organic molecules. The Google team then used the quantum echoes algorithm running on the Willow chip to simulate the quantum interactions within these molecules and predict their structure. The results were astounding. Not only did the quantum computer's predictions perfectly match the known results from traditional NMR, but it went even further. Because the quantum echoes method is so sensitive, it was able to act as a molecular ruler, detecting faint, long-range interactions between atoms that are completely invisible to classical tools. It revealed hidden details of the molecular architecture, like finding secret passages in a house you thought you knew completely. This wasn't just a validation. It was an upgrade. It demonstrated that quantum computers could become an essential partner to existing scientific methods, extending their reach and revealing a deeper layer of reality. This collaboration marks a profound shift in how we should think about these machines. For decades, we've called them quantum computers. But perhaps a better name for now is quantum instruments. Think about the invention of the microscope. It didn't just allow us to calculate things about microbes faster, it allowed us to see them for the first time. It opened up an entirely new, invisible world. The telescope did the same for the cosmos. It didn't just compute the orbits of planets. It revealed the moons of Jupiter and the rings of Saturn. The quantum computer, powered by algorithms like quantum echoes, has now become a similar kind of instrument. It's a quantum microscope, a new lens that allows us to peer directly into the molecular and atomic realms with unprecedented clarity. It's not just a machine for crunching numbers. It's a tool for observation, an extension of humanity's senses, allowing us to explore the fundamental fabric of nature in a way we've only ever dreamed of. So, what does this new quantum vision mean for our daily lives? The implications are staggering and will unfold over the coming years, touching nearly every aspect of technology and medicine. Consider drug discovery. Right now, developing a new medicine is a process of painstaking trial and error that can take over a decade and cost billions of dollars. Scientists have to synthesize and test thousands of candidate molecules to find one that interacts with a target protein in just the right way to fight a disease. But what if you could skip most of that? With a quantum instrument, you could simulate the exact quantum interaction between a drug molecule and a protein with perfect accuracy. You could design the perfect key for the biological lock on a computer screen, eliminating years of guesswork and failed experiments in the lab. This promises a future of rapidly designed, highly personalized medicines. Or think about materials science. We need better batteries for our phones and electric cars. We need more efficient solar panels. We dream of room temperature superconductors that could transmit electricity with zero loss, revolutionizing our energy grid. All of these challenges boil down to understanding and engineering the quantum behavior of electrons in materials. Classical computers can only approximate these interactions. A quantum computer can simulate them directly, allowing us to design these revolutionary materials from the ground up, atom by atom. From creating new catalysts to pull carbon out of the atmosphere, to designing more efficient fertilizers to feed the world, the ability to precisely model and manipulate the quantum world is the key. This breakthrough is the starting pistol for a new race to solve some of humanity's most pressing problems. This is the moment that will be written about in textbooks. This is the birth of verifiable quantum advantage. Let's break down those words. Advantage means the quantum computer is not just doing something esoteric. It's solving a valuable, real-world problem faster and more accurately than any classical machine could. It's the shift from a theoretical curiosity to a practical tool. The word verifiable is the true cornerstone of this new era. It means we have crossed the chasm from belief to knowledge. The results can be trusted. The science is repeatable. Another quantum computer of similar quality could run the same calculation and get the same answer. This establishes a benchmark, a gold standard that moves the entire field forward on solid ground. This isn't just an incremental improvement. It's a paradigm shift. For 70 years, our entire digital world has been built on the foundation of classical computation. We have just laid the cornerstone for a new foundation, one that embraces the weirdness and wonder of the quantum realm to solve problems we previously thought were unsolvable. So, what's next on the horizon? With this milestone achieved, Google's focus is already shifting to the next great challenge on their roadmap: building a fully error-corrected quantum computer. The battle against decoherence is not over. The quantum echoes algorithm is an incredibly sophisticated way to extract a clear signal from a noisy system. But the ultimate goal is to make the system itself inherently stable. This is the quest for the logical qubit. A logical qubit is a revolutionary concept. Instead of relying on a single, fragile physical qubit, you encode the information across a team of many physical qubits. These qubits work together, constantly checking on each other and correcting for any errors that creep in, much like how data on the internet is sent in redundant packets to ensure the message gets through intact. A logical qubit is a self-correcting quantum unit, designed to be robust and fault-tolerant. Building stable, long-lived logical qubits is the key to unlocking limitless scalability. It's the path from the powerful but delicate instruments of today to the universal, fault-tolerant quantum computers of tomorrow, machines that can run calculations of arbitrary length and complexity without succumbing to errors. The journey is far from over, but the path is now clearer than ever. Perhaps the most exciting part of this announcement is the timeline. The age of practical quantum computing isn't a distant, abstract dream. It's beginning right now. The quantum echoes breakthrough proves that we don't need to wait for a perfect, fully error-corrected machine to do useful, world-changing science. With these new verifiable algorithms and the exponential progress we're seeing in hardware, the first real-world applications are projected to be within our grasp in the next 5 years. Think about that. By the end of this decade, the first drugs designed by a quantum computer could be entering clinical trials. The first breakthrough materials simulated on a quantum chip could be finding their way into our technology. We are living in the early adopter phase of the most significant technological revolution since the invention of the microchip. The progress will be fast, and the impact will be profound. We are standing at the foothills of a mountain range of discovery, and for the first time, we have the tools to begin the climb. For decades, the central question of this field has been, can quantum computers ever truly work and be useful? With the demonstration of verifiable quantum advantage, that question has been answered with a resounding yes. And so, a new question takes its place, one far more exciting and profound. What world-changing problems can we now solve? The age of theoretical quantum potential has ended. The era of practical quantum application, the quantum era, has officially begun. This story isn't just about technology. It's about a fundamental expansion of human capability. It's a lesson that with persistence, ingenuity, and a willingness to embrace the strange rules of the universe, we can build tools that allow us to see farther, understand deeper, and solve the unsolvable. The lesson for our own lives is one of perspective. So often, we are faced with problems that seem impossibly complex, limited by our current way of thinking. This breakthrough teaches us that sometimes the solution isn't to just think harder, but to find a completely new way to see the problem. It's about building a new lens, a new instrument that reveals a hidden layer of reality we never knew was there. So I ask you, what impossible possible problem in your life, your community, or the world could be solved if you could just find a new way to look at it? What could quantum echo from your past actions could be telling you something profound about your present reality, if only you knew how to listen? Thank you for joining me on this incredible journey to the edge of computation and discovery. I hope it has left you with a sense of wonder and optimism for the future we are all about to build together. If you found this story as inspiring as I did, please consider subscribing to the channel for more deep dives into the science and technology that are shaping our world.